Welcome everyone to the last AMS colloquium of the semester. We're very fortunate today to be graced by our very own AMS grad students who are going to tell us about the research that they're working on. And so I'm your host, Paul Constantine. Everybody here knows me, I think, but we'll get started with Nick Fisher. Nick, here's this. And Nick is a grad student in the AMS department. And by way of introducing yourself, Nick, how about you tell me what's the most interesting thing that you did this semester?
This semester?
Yeah.
Did a lot of grading.
A lot of grading. All right. So grading was interesting this semester, and with that, I give you Nick Fisher.
Okay, so I'm going to talk about orthogonal spline collocation for PDE constrained optimization. In particular, we're focusing on applying orthogonal spline collocation discretizations to develop numerical methods. So we're not going to get into the theory of optimization. Okay. So first I'll introduce orthogonal spline collocation. Then we'll work on this linear problem. And for the linear problem, we'll look at preconditioning for MINRES. And then we'll work on the nonlinear problem, in which case we'll need to apply Newton's method in order to solve the resulting linear system. Okay. So first, there's going to be some definitions that are going to be important, and they're going to show up throughout the presentation. We're going to start with a uniform partition of our interval, AB. And then H here is going to be the step size, and N will be the number of subdivisions. So next, the sort of relevant function space is the space of C1 piecewise polynomials. In particular, we're focusing on third-degree polynomials. The reason why we want to do that is we can leverage the things we know about the resulting collocation matrices, the spectral properties of the collocation matrices resulting from piecewise Hermite cubic basis functions are well known, and we're going to leverage that in a bit. And M0 here just denotes that homogeneous boundary conditions. So the next important piece is our set of collocation points. So we're going to take the 2-point Gauss, the nodes of the 2-point Gauss-Legendre quadrature, and then we're going to put them on each subinterval of our partition. So what I mean is we're going to take some partition of AB, call this x0, x1, x2. Then on each subinterval, we're going to have the two nodes of the Gauss-Legendre quadrature. And this will be taken all together our set of collocation points. Okay, so to explain orthogonal spline collocation, I'm going to just look at this simple 2-point boundary value problem. So we have U here, right, satisfy this differential equation with our little linear operator. We can have non-constant coefficients if we like. Again, we're going to be focusing on homogeneous boundary conditions. So the OSC solution then is U in our space of C1 piecewise polynomials, such that it satisfies the 2-point boundary value problem at the set of collocation points. Okay, so what we're going to do is take a basis expansion for our solution, and we're just going to insert it into the differential equation. And then what we should get out is a linear system for all of the coefficients. So we're going to do that, and what we get is these special matrices, these almost block diagonal matrices. So for instance, if we have n of 4, then this is going to be the resulting matrix. So the fact that our top and bottom blocks are a different shape than the interior blocks is because of the fact that we chose to do this with homogeneous boundary conditions. Okay, so what's important here, just to point this out, is the columns refer to the basis functions, J here, and then the rows are the collocation points. Okay. And just to point this out, there are efficient methods for solving ABT linear systems, in particular Collo. All right, so this is what we get. When we plug everything in, we just get this one big linear system where these diagonal matrices here just keep track of the contribution of our coefficients. And what we get out is the coefficients for the cubic spline interpolant. And what we put in is just F evaluated at the collocation points. Okay, so that's orthogonal spline collocation in a nutshell. We will be doing two-dimensional problems, but it just follows the standard sort of tensor product formulation, so I'm just going to skip that. Okay, so here's our distributed control for Poisson's equation. So this is our cost functional, where this function u hat is known, and we're going to allow u and f to vary such that they satisfy Poisson's equation as a constraint and minimize the cost function. So this term here is the Tikhonov penalty term, which ensures the well-posedness of the problem. And I'm not going to go into too much details where this term comes from. And this parameter beta here is the penalty parameter, and it's usually taken, if you check the literature, to be something like 10 to the minus 2. Okay. So now we're going to do the same thing. We're going to take our, we're going to look at the collocation equations, and then we're going to put in our basis expansion, and what we get out is this guy, the discrete Lagrangian. Sorry, the discrete constraint function. So alpha here is just a number, it's the norm of b, and b is just u hat evaluated at the collocation points. Okay. So now we can construct the discrete Lagrangian. So this isn't that much different than what you learned in Calc 3 when you did constraint optimization. So here's the constraint function, and then lambda, our Lagrange multiplier, times the constraint, right, where this solves Poisson's equation. All right, so what we get using the KKT conditions is just this big linear system. Just a note here, if we had non-homogeneous boundary conditions for a Poisson equation constraint, we would have another vector here that contains the contribution of the boundary conditions. So what's important about this matrix is that it's symmetric, which is somewhat surprising given that the collocation matrices aren't symmetric, but it all comes out in the wash. And also that it has this very special structure. So if we partition dimension like this and like this, we get a saddle point system. And what's nice about that is we know very good preconditioners for saddle point systems. All right, so this preconditioner here contains all the stuff on the main diagonal. Right, this guy 2 beta I and B transpose B, and then this guy here is just the Schur complement of this matrix. Okay, so what's nice about this preconditioner, there's a paper, it's Murphy, Golub, and Wathen. It's a short paper, it's 3 pages, and then the last page is just references. So what's nice about that paper is it shows that this matrix, we take P1 inverse A, and this has 3 eigenvalues. Okay, so we know that if we use this as our preconditioner for MINRES, MINRES will converge in at most 3 iterations. Okay, so there is another paper that I'm really building off of this on, called by these authors Rees, Dollar, and Wathen, and they investigated this precondition. So what we'd like to say is something about the eigenvalues of P2 inverse A. Right? What does that give us? Well, it turns out because I chose to use these piecewise Hermite cubic basis functions, that we can say something very particular. In fact, that if lambda is an eigenvalue of P2 inverse A, then it falls into one of these 3 categories. So we know that the eigenvalues are clustered, and moreover, they remain bounded away from 0 as h goes to 0. So all of this together suggests that this should be an optimal preconditioner, i.e. that MINRES should converge in a number of iterations that's independent of subspace. Okay, so here's just to check, throw in some numbers and see what we get. So these are the eigenvalues of P2 inverse A. So the blue lines here are these bounds that we found. And then the dots are the actual eigenvalues. So we see for these simple examples, we do get the expected result. All right, so we can run some numerical experiments and check to see that our preconditioner is actually optimal. So we're going to do that in 1 and 2 dimensions, just for fun. And we're going to pick some particular choices for you. So this is what we get. So I swept several different values of beta, and then these make these. Sorry. This axis here is actually counting backwards, which I know is annoying, but it's standard for reasons I don't understand. So we start here. This is the largest h value. This is actually h equals 1. So really we can just chuck that point out. It's really not that interesting case. So this is just fitting a 1 cubic polynomial to the whole domain. And so really we can just ignore this point. But this is what we get. So for beta, as I said, 10 to the minus 2 is commonly chosen, and we see we get nice constant iteration counts in 1D and in 2D for MINRES. Then as we take beta smaller, we still get, so this is 5 times 10 to the minus 5, we still get constant iteration counts for MINRES. But finally, when we take beta to be really small, things start to break down. But this should make some sort of sense if we go back to what our preconditioner looked like. We had this term here that goes like 1 over beta. So at some point, we can't ignore this contribution. And that's what we're seeing here as MINRES breaks down. Okay? So that's a nice, easy linear problem. So we can try to do something a little more interesting and look at the distributed control of Burger's equation. So we're going to do this all in 1D, but that's not particularly important. Again, we have u hat here is known, and then we're going to let u and g vary. Again, we have another penalty term. Okay. So this parameter here we've added in front of the first derivative is the viscosity. Okay, so we can look at the collocation equations again. We take our basis expansion again. We stuff it into the collocation equations and get a linear system for the coefficient. Sorry, a nonlinear system for the coefficients. So this guy here is nonlinear, and it involves the product of BU and CU, right? And the element-wise product of these two vectors. Okay, so once more, we're going to start the discrete Lagrangian. So we have our objective function, and then lambda times our constraint. And again, we're going to look at the KKT conditions, except this time we get a nonlinear system of equations. All right, so we're going to have to try it out. So what we did is this. So this is sometimes called the Newton-Lagrange method or the Lagrange-Newton method. Really, it's just a simple form of SQP, sequential quadratic programming. Okay, so the idea is this. We're going to pick some initial guess for G, U, and lambda, say 0. Plug it in and solve this linear system. That'll give us the updates. We take the new G, U, lambda and solve the linear system again. Then we will terminate the Newton iteration when the norm of the gradient of the Lagrangian here and the norm of the constraint are things in Pollux that we can choose. Okay, so one more thing here. This guy. So when we take the derivative of our nonlinear term, we get this funky looking thing. Also, there's I've sort of pulled a fast one on you. So this guy isn't quite right. So this term here, this 2-2 block, comes from the Hessian of the Lagrangian. 2 minutes. Oh, okay. So this guy here comes from the Hessian of the Lagrangian, and what we've done here is ignore the contribution of the nonlinear term to the Hessian. So we're going to trade sort of computational efficiency for possibly slower convergence of Newton's vector. Anyway, we're going to do the same thing. We're going to look at this block diagonal preconditioner, and then we're going to track MINRES iterations across Newton iterations. So here, for different viscosities, we take our preconditioner and we run MINRES. So this converges in 3 Newton iterations for a viscosity of 1 in about 12 or so MINRES iterations. So as we decrease viscosity, in some sense this becomes a more difficult problem, since the effect of the nonlinear terms becomes dominant. And then we see that Newton iterations take longer to converge, as does MINRES. Okay, so so some things we could do in the future are just make this a more robust optimization method. We can accelerate the convergence of our preconditioners using Navier-Stokes. Bialecki and I have been working on OSC methods for Navier-Stokes equations. We can do PDE constrained optimization with Navier-Stokes as the constraint, say. Okay, so with that, I'd like to thank a few people. So Dr. Bialecki and I have been working on methods for Berger's equation with the orthogonal Spline collocation, and of course, my collaborators at Zandia, Eric Sear, and then Dennis Rizal has been very helpful in the past couple of weeks putting this all together. Okay, that's it. Any questions?
Time for one quick question.
What's up? Why you drop the I term? That should be easy.
Yeah, no. So the idea here is that I'm not trying to construct the best possible optimization method using an orthogonal Spline collocation distribution. The idea is to follow what Riesdahl and Wathen did and see if we get the same result.
But do you get computational speedups by removing the I beta term?
No. This here, let's just look at the iteration counts. We know that the other preconditioner is guaranteed to converge in at most 3 iterations. The best one is 7. So I think in their case, what they had here was, in place of all of these identity blocks, when you do the finite element discretization, you actually get mass matrices. So then, for finite elements, this isn't identity, this is a mass matrix. So their argument was inverting this mass matrix was expensive. In our case, it's just identity. So, yeah. So I'm not sure. I would guess that this is a pointless exercise in terms of getting the best possible optimization method for orthogonal Spline collocation, but that's not what I was interested in doing. Right? I just wanted to see if I followed Riesdahl or Wathen, do I get this result, basically.
Okay.
And thank you.
Great, thank Nick.
Yeah.
Thank you, Nick. Up next, we have Andrew Glaws, another PhD student in our department. And Andrew, by way of introduction, I will ask you, what do you find most interesting about this topic in one sentence?
In one sentence. I just like that it is kind of combines a few different fields that were sort of new to me, so I got to learn a few different things all at once.
Cool, lots of things all at once. Andrew Glaws.
So I'm going to talk about inverse regression methods for sufficient dimension reduction in deterministic models. This is work that I've been doing with my advisor Paul and also with Dennis Cook, who is at Minnesota. So I'm just going to kind of introduce a problem for sufficient dimension reduction, which is kind of a regression problem. So if we have just some samples drawn from a joint distribution here, where the y's are scalar responses and the x's are going to be a vector of predictors that's, we're going to say it's got m entries. We want to study this conditional distribution y conditioned on x. So basically we want to, for fixed values of x, what's the distribution on y's? And when we talk about study, it could be things like doing some sort of regression, like fitting a multiple linear regression. It could be studying statistical information, such as trying to compute the CDF of this conditional distribution, or just an expectation or variance or something like that. Or we could be interested in doing graphical investigation, which would just be kind of scatter plots of the y's against various x's. But all of these things get more difficult as the number of predictors, m, increases. So the point of sufficient dimension reduction is to try to reduce m, but still maintain the information in the problem so that these studies are useful. So sufficient dimension reduction kind of takes advantage of an old idea in statistics just known as sufficiency. Sufficiency or sufficient statistic comes up where, let's say we have some samples here drawn from some distribution, which is characterized by some parameter theta. Then we can calculate some statistic of from the data, and we can say that statistic, theta hat, is sufficient for theta if no other statistic from that data can be calculated, which gives us more information on theta. So like an example of that is if we have data drawn from a normal mu sigma squared, and we assume we know this variance, then just the traditional sample mean is sufficient for the distribution mean, which just means if we know this mu bar value, we can't learn anything else about mu from this set of data. And so sufficient dimension reduction kind of extends this idea to the regression problem. So again, we have some set of data here from a joint distribution. We've got our predictors and our response. And so what we're kind of curious about is, let's say we have some matrix here that's m by n, and can be less than or equal to m, so it's potentially a tall matrix. So if we do an A transpose X, we get a vector of length n, and we want to consider this conditional distribution of y conditioned on these reduced variables. And basically SDR is a framework for saying under what conditions can knowledge of this conditional distribution provide insight into the actual conditional distribution y on X that I'm interested in. So the main tool for doing this is called a dimension reduction subspace. So the idea is if we have our predictors and response, then DRS is defined as the column space of a matrix A such that this property holds. So just unpacking this property, it's known as conditional independence. It basically says that if we know this A transpose X, so if we know just the reduced predictors, then Y is going to be independent of the original predictors. We don't gain any knowledge by knowing the full X if we know this A transpose X. So that's kind of the parallel to sufficiency in this case. One of the things that's really useful about this is that if this is true, then this is equivalent to saying that the CDF of the conditional distribution y on X is the same as the CDF of the reduced conditional distribution, which means all the statistical information from one can be used to inform the other. The other thing that's useful just when studying these is that the matrix is not unique in defining dimension reduction subspace. So it's truly the subspace we're interested in. Basically, if we have two matrices with the same column space, then we have conditional independence for either. So we focus our study not so much on the matrix, but just on the subspace. Also, these dimension reduction subspaces are not going to be unique for any particular problem. So for instance, by the way we've defined them, every problem is going to exhibit the trivial subspace, which is just all of Rm, which doesn't actually reduce the dimension of the problem, but it just says it always exists. Furthermore, if we have some sort of dimension reduction subspace, which is generated by this matrix A that is a tall matrix, we can always add a column to it that's not in the column space of it, and that creates a new dimension reduction subspace. But our new one has a larger dimension than the original one, so it doesn't seem very beneficial to look at that one, seeing as our goal here is dimension reduction. So what we really want is a unique and optimal dimension reduction subspace, and optimal being in the sense of one with the least dimension. So we define what's called a central DRS, and this is going to be a dimension reduction subspace which is contained within all other dimension reduction subspaces. Not every problem is going to have a central DRS. You can kind of construct some interesting examples where they don't exist, but there is also conditions for when they do exist that are relatively mild. If your problem does exhibit a central DRS, then just by looking at this, we can see that that central DRS is just going to be the intersection of all other DRSs. And so why it's useful is just this theorem here, which is that if you have a central DRS, then it's the unique minimum DRS for your problem. So the whole goal of sufficient dimension reduction is going to be trying to find this central DRS. So in the central DRS, there's a lot of properties. It's been studied pretty thoroughly. I'm kind of skipping over a whole bunch of them. I want to talk about this one because it's useful in the numerical methods that come up to try to estimate it. So if you have a central DRS for a particular conditional distribution and you have some function of your response, then the central DRS for the new conditional distribution for that mapped response must be contained within your original. And this is useful because what we're going to introduce is some sort of slicing function here, which is just partitioning the range values into H slices and then kind of mapping each Y into an index for which slice it falls into. And then if we define this as our mapping, we get to use this property. So this will come into play when we look at numerical ways of finding the central DRS. And these numerical techniques are going to take advantage of what we call the inverse regression. What we're trying to find is, or what we're trying to study is Y conditioned on X. But what we're going to use to study that is going to be X conditioned on Y. So we're going to look at fixed values of Y and consider what the distribution of the X is for that. And the reason we do this is because it kind of simplifies the problem. We can view this as M univariate conditional distributions for each of the predictors, which simplifies the problem. And in particular, what we're going to be interested in is called the inverse regression function, which is just taking this conditional expectation of your inverse regression. And this can be really thought of as a curve through m-dimensional space parameterized by your response values. And what's going to be really neat about this curve, which I believe is the next slide, is this property, which essentially says that under certain conditions, which are relatively mild, that rely on the distribution of your predictors, under certain conditions, this curve through m-dimensional space is going to be contained within an n-dimensional subspace, which is to say that that curve lives within the central DRS. So it might not pass through all of the central DRS, but it's definitely contained within it. So if we can get some insight into this subspace, which is just the column space of this covariance matrix, then we know we are able to uncover at least part of the central DRS. So we consider our slicing function from earlier, and we have this property from our slicing function. So if we combine kind of this idea and this idea here, we get this, which basically is the essence of what's called sliced inverse regression, which is one algorithm for estimating the central DRS. So sliced inverse regression is just a method of taking these samples that we have of the response and the predictors and using it to estimate this subspace. Similarly, we have another algorithm called sliced average variance estimation. And again, under some assumptions, they're just related to the distribution of these predictors. We have this containment, where instead of looking at this expectation of the inverse regression, we look at this covariance here. And this subspace is going to be contained within our central DRS as well. So if we can estimate this subspace, we can get some insight into the central DRS. And so we again apply our slicing. We get all these containments here. So the save algorithm is essentially constructing an approximation of this subspace. And just briefly, the reason we kind of have these two methods right here is that they are known to perform better in different situations, although you probably don't know the kind of structure that exists in your problem until you've already tried it. For instance, like the SIR algorithm really struggles when you have sort of symmetry within your problem, whereas save would perform better in that case. So it's usually recommended that you kind of try them both, and they're both very similar, so you can almost run them in parallel to each other. So what we're interested in is looking at deterministic functions. So instead of having some sort of random data coming from a joint distribution, we have a deterministic relationship y equals f of x here between our inputs and our outputs. And we also have some sort of known density on our inputs. And now we wish to study this problem, which could be optimization, constructing a surrogate, doing some sort of UQ. And again, like the regression problem, these things get more difficult as m increases. So what we want to understand is, can we apply these techniques for sufficient dimension reduction to this problem in order to solve some of these same dimensionality issues? So remember that sufficient dimension reduction is reduces the dimension without any sort of loss of information on your regression problem. But what that means in a deterministic framework is that your function has this sort of form, where your y of f of x can be replaced by some new function g of a reduced number of inputs.
Andrew, what do you call this deterministic problem? What do you call it deterministic if you have an x that is random?
Well, it's because we have this deterministic relationship between between x and y. Whereas
Yeah,
before,
it's random relation.
but the deterministic part comes from if you chose for a specific value of x, you're going to get the same y every time. Whereas before, with the same predictors, you could get various values of y. So there might one way to think of this problem would be to have like a plus a noise term for the regression type of problem. So that's where the deterministic name comes in, is that the relationship here is deterministic between the two.
Well, if you condition on x is deterministic because it's no longer random, but it's not random.
Let's save questions till the end. Thanks. Because you got 1 minute.
Okay, yeah, so the idea is that if we do dimension reduction without any loss of information, which is sort of similar to this sufficient dimension reduction, it takes this form, and it just so happens that this form is known as a ridge function. So this is just a definition for a ridge function, which is now what we're looking for. It's kind of the parallel here for SDR, or for the dimension reduction subspace. And basically we're answering a couple questions right now. That is, how does the theory of SDR translate if we have this deterministic relationship between inputs and outputs? And if we were to use our deterministic relationship here to construct a data set that looked similar to what we had in the other problem, how would the algorithms behave, and would we be able to use them in order to construct, or in order to solve this ridge recovery problem, which is, could we find this A? And so that's kind of where we're working on right now. Just going forward, this is the big thing we want to look at going forward, is this idea of, since we have some sort of deterministic function here, and we can actually select our x's, they're not just given to us as data, but we can choose them. We can exploit this nature and select our x's such that we can more accurately compute these subspaces. So we don't necessarily just have to, we can kind of come up with alternative subspaces or alternative algorithms that estimate these subspaces. And that's one of the big goals. And then there's some other things we also like to look at eventually. But that's the big one.
All right, thanks, Andrew. I would say we have time for questions, but that would be a lie. We don't. So if you'd like to discuss this with Andrew later, I encourage you to. And otherwise, thanks so much, Andrew. Up next, we have Zach Gray, another PhD student. I meant to say that both Andrew and Zach are the Freiberg Fellows. That's how they're funded for their PhDs. Zach, by way of an introduction, what do you expect the ultimate impact of this work will be?
Hopefully some sort of improvement in efficiency for the industry of aerospace engineering in terms of how they manufacture things and how they interpret their simulations.
So making better spaceships.
Making better rockets and jets and stuff.
All right, cool. Zach.
All right, so we're going to talk about ASAP, active subspaces of airfoil parameterizations. I'll very briefly go through what I mean by airfoil, in case nobody's really familiar with that term, and in particular in the context of transonic flow regimes, so these types of fluid flows around the airfoil. Then we'll talk about airfoil representations. From that point, we're interested in finding these low-dimensional structures of these airfoil representations. There's a design procedure that most engineers would follow in terms of trying to solve the type of problem which Andrew mentioned, something like surrogate modeling, optimization, uncertainty quantification, where the reduction in the dimensionality is of a benefit. And then we'll talk about a specific case where if I don't have gradient information, how can I solve that active subspace problem? I'll talk about some results I have for a very specific parameterization. We'll show some convergence. We'll talk about CST's active subspaces, and then show the implications of the types of approximations and perturbations we can make to these airfoil shapes. And then I'll just conclude. Okay, so what we have here is some pilot in an F-18 Hornet. Thank you, Marcos, for the picture off of Flickr. And they are presumably going somewhere very, very quickly, and also listening to Kenny Loggins, hence the music choice at the beginning. But what we see is forming here is we see this condensation cloud that's forming around the jet. That's because the jet is traveling relative to its ambient fluid. It's traveling in this transonic flow regime, which is a combined flow regime that has subsonic and supersonic properties. In particular, this area where the condensation is gathering, those are the supersonic portions of the flow. So the flow in those regions is moving faster than the speed of sound. And everywhere else would be subsonic. So this is a transition to supersonic flight. We can model that behavior using Euler's equations. Euler's equations is a great approximation when we're working with air, which is relatively incompressible, and we're interested in, relatively inviscid, and we're interested in the compression properties of the fluid as we move through it. So what we see here is on the aircraft, if we took a slice through the wing of the aircraft, and we looked at that 2D representation, we would get an airfoil. So this black shape is the airfoil that we're interested in, and we're interested in modeling the fluid behavior around that. All right, so the airfoil as a shape. I think it's interesting to mention that the airfoil looks like a rotated teardrop manifold, but in particular, talking about the airfoil as a manifold allows us to make one specific assumption in its representation, which is that it can be charted. And that means that essentially I can partition the shape into two representations by functions which satisfy a variety of properties. So we have some domain, L, which is going to be scaled 0 to 1. So this is non-dimensional, and that's going to map to our representation of the shape, which we'll call the upper surface, S1, and we'll call S2 the lower surface. There's some characteristics of this shape that are important to us. So we came up with a set of assumptions that were reasonable for being able to construct these airfoil shapes. So in particular, if S1 and S2 map from 0, 1 to the reals, we want that shape to be finite. Obviously, this airfoil has to be manufacturable to some extent. So if it's essentially bounded, that is a good criteria for restricting S1 and S2 to a function space. We also expect S1 and S2 to be smooth on the interior of our domain. So we don't really want to make airfoils that have these discrete jumps. Those are also not considered manufacturable. We want the airfoil to be feasible in the context that it does, once again, have to be manufacturable. So the upper shape has to be strictly greater than the lower shape on the interior of its domain that it's represented on. And then we also have this fixity condition. At the leading edge, both functions at 0 should map to 0. Optionally, we could fix the trailing edge point. So when I say leading edge and trailing edge, I mean this neighborhood around 0 or this neighborhood around 1. So optionally, we could have this restriction as a constraint on building these shapes. So those are some rules. There is a specific class of airfoils which engineers in the aerospace industry are typically interested in, and those are round nose airfoils. So if we talk about airfoil representations, we basically write it out in terms of a basis representation, where A is some matrix which represents our coefficients, and it will map to the respective surfaces. So we're going to just introduce an index for S1 and S2, and these phi's will represent our basis of choice. So types of parameterizations we can introduce to represent airfoil shapes. We could use a Karhunen-Loewe if we had some sort of uncertainty associated with the shape. This is a very common choice if we're doing a UQ type problem and we want to study variations in lift or drag or any other fluid property over the airfoil if the airfoil was random. We could use parametric spline representations over the entire airfoil. or we could use some other basis expansions. What I mean by that is that essentially all three of these can be described as a basis expansion. But other basis expansions are ones in which they are informed through some process by an engineer who has intuition about the problem he or she is trying to solve. So we wanted to study those specific expansions and see if there were properties associated with those expansions that were advantageous to representing airfoils. So those two are actually going to be called parsec and CST. Parsec is roughly to be translated to parametric sections. It's a strange way to put it. And CST, which is a class shape transformation. Also kind of a strange name for what they chose, but in particular, a parsec representation is an expansion of 6 different basis functions, and these basis functions look to be all in terms of half powers. So that's going to be important when we start discussing the implications of the round-nosedness of the airfoil. So when we're in the neighborhood of 0, these half powers are going to drive this round nose behavior, which I'll talk about next. What's interesting for parsec is it was chosen to have exactly 6 basis elements. Those 6 basis elements were chosen because there are exactly 6 physical constraints that the engineer invented for which they wanted to parameterize these coefficients. So the choice of basis functions and number of basis elements in this case was very specific to the problem they were motivating in terms of representing the shape. Alternatively, a more generic representation would be CST. Now they call it a CST method because there is a factorization of class functions and shape functions. The class functions are these powers that would be represented here, where we have the square root of L times 1 minus L. This is going to basically govern that shape that we saw initially. So something that maps from maps to 0 at 0 and maps to 0 at 1. But then we want to bias that distribution by some sort of analytic representation. So there is some shape function which we multiply that. However, through very simple algebraic manipulation, we can show that for the cases when m equals 4, if the coefficients in these expansions are the same, they're the exact same parameterization. So there's absolutely no difference between the two, given a specific choice for the dimensionality here. The nice thing about CST is it allows us to be flexible with the number of dimensions we choose in our basis representation. So I can add arbitrarily however many terms I want. In this case, I have m+1 coefficients that I would use to parameterize the shape. So as I mentioned, those two shape representations have the exact same basis expansion. What they immediately make kind of evident is this intermediate scale, is this half power scale. So if we do a simple change of variables, we plug the half power in, and we call that our scale of interest in terms of the shape. Then if we consider for some small epsilon, some epsilon much less than 1 greater than 0, such that z is order epsilon, we can essentially approximate this shape relatively well by just some linear function in z, that intermediate scale. Now this is where the round-nosedness of the airfoil comes into play. Why half powers? Well, if I put an epsilon ball near the origin, so actually epsilon away from the origin, I can actually represent that circle in terms of this intermediate scale. And if I do the same type of low-order approximation of the circle, I can immediately find what the value of this coefficient should be, such that I emulate some sort of circular or round-nosed looking shape in the neighborhood of 0. So A1 should equal the square root of 2 epsilon, and epsilon is now related to this physical quantity. We can interpret it as some sort of radius associated with the nose of the airfoil. So you may be thinking to yourself, wow, you're approximating a circle with a line. That sounds horrible. But let's take a quick look at that. If we plot just over our original scale, we can see here's our epsilon ball of interest. We've zoomed in onto the neighborhood of the nose of the airfoil. And the square root would represent, for some arbitrary coefficient, in this case, I don't know what the coefficient was, I can compute the radius of the epsilon ball and the associated square root function. This is just that coefficient times z. And it actually well approximates the airfoil in that region. Not so much interested in a good approximation of the circle, but this is what gives us the round-nosedness. We want changes in the slope of the airfoil near 0 to behave like this square root function. It's a little bit more pronounced to see this if we actually plot over the intermediate scale. We can see that the epsilon ball changes to this stranger looking shape. It does begin to look linear when we are in the neighborhood of 0. and in particular, that linear estimate and finding the coefficient A1 as the square root of 2 epsilon becomes, looks like a much better approximation over that intermediate scale. So we've revealed this important scale, and we've related that scale to an actual physical quantity, something that an engineer would be able to interpret or go measure. All right, so now we have a design procedure. We have the parameterizations, or we have basis expansions which represent the shapes. We want to parameterize those expansions. I said previously that we would use a set of 6 equality constraints to construct an invertible matrix C, and then we would assign values into the R6 vector for P to then compute coefficients. So parsec is beneficial because we can directly relate those constraints which are physically interpretable. Those are things like the radius of the leading edge, a slope of 0, the slope of the trailing edge, the coordinate location at an intermediate point. So they're physical quantities that are relevant. However, in CST, we'll just assume that our parameterization is just changing the magnitude of the coefficients in each expansion. So our design vector in this case will just become twice the number of coefficients, and we'll assume each expansion for the upper and lower shape has the same number of terms. So in this case, our expansion has 5 terms, and we combine those together for a design vector, which is a total of R10. Once we parameterize the shape, we generate them, then we mesh them, or we discretize the complement of the space around the airfoil where the fluid lives, and then we'll compute functionals of interest like lift and drag by simply doing line integrals over that boundary of the airfoil to give us an indication of dimensionless quantities of force, so how much lift am I creating from the airfoil and how much drag is being induced from the wave properties of Euler's equations. And that is what gives us this composition. So we have a design vector that gives us shapes that consequently gives us computation of a lift or a drag value. So with this composition, we want to do active subspaces on it. So given the parameterization we've chosen, we now have a mapping from Rm in our design vector to some scalar quantity of interest. We do also choose bounds for x, and it's very important that in application, these bounds are going to drive the behavior and what kind of subspaces and what kind of low-dimensional subspaces we can actually find quite strongly. And we scale that to a -1-to-1. So x has now been scaled from some original dimensional space to a -1-to-1 hypercube. And in this case, we've done that arbitrarily. So I know that it's important to pick these bounds, but we've done so by taking a nominal shape and then perturbing it plus or minus 20% in an example we'll show here. So we have some bounds, then we construct this C matrix, which is symmetric, positive, semi-definite. So it has real non-negative eigenvalue decomposition, which is represented by this diagonalization. Rho is some density of x with support on that -1-to-1 hypercube. The goal here is to then find some approximation of our quantity of interest that was originally represented in the m-dimensional or otherwise high-dimensional space, and project those parameters down to a lower dimensional space using W1, which is Rm by n, where n is less than m, and W1 is obtained from a partition of the eigenvalue decomposition. However, in some cases, engineers don't have, they're not readily accessible. They cannot obtain the gradient, excuse me. If that is not available, then we suppose that f can be well approximated by a quadratic model. So this is now essentially proposing a regression of a collection of pairs of parameters and function evaluations. Once we have that quadratic approximation, we can then assume or choose x to have a density which is uniform on the hypercube, and then we get this matrix which results, and then it has an approximation of its eigenvalue decomposition. And that is how we can get these lower dimensional subspaces which we wish to project into. So if we look at some convergence, if we took up to 6,500 samples, and I was actually interested in a subspace error, this is just a representation for how orthogonal is W1 in terms of the total number of samples versus W2, which would be the remaining partition of that original W matrix. So if I look at that error, we do see a nice 1/√n convergence for both parameterizations, but on average, CST tends to have less subspace error than parsec. So let's just study CST briefly. Here's the eigenvalue decay for the CST in terms of the non-dimensionless quantity for lift and the non-dimensional quantity for drag. And we see a large gap between the first and second eigenvalue. That would indicate to us, given an error bound that we have, an analytic error bound, that a good choice for estimating the low dimensional subspace would be a dimension of 1. Similarly, for drag, the large gap happens between 2 and 3, so a good choice would be a low dimensional subspace of 2. If we then project our data, 6,500 samples, into those low dimensional subspaces, and I then plot my quantities of interest, so my lift versus my active variable, and my drag versus my other 2 active variables, we get these really strong trends for being able to well approximate lift by a one-dimensional subspace and well approximate drag by a one-dimensional subspace. So this is an outstanding result. Furthermore, if we look at the subspaces, we notice that only the leading coefficient in the respective expansions for the upper and lower surface were significant. All other coefficients are 0 when we project our data into these lower dimensional spaces. What that means is, given the relationship that those leading coefficients represent this type of scaling to a radius at our leading edge, we can relate these subspaces to actual physical changes in the airfoil. Furthermore, the lift subspace, the eigenvector for lift, is exactly the same as the second eigenvector for drag. That means that the first eigenvector for drag, which represents the direction in which drag is changing the most on average, is actually orthogonal to how lift is changing the most on average. That's phenomenal, because now I can study things like perturbations to the airfoil in terms of that first eigenvector for drag, but additionally in terms of a perturbation to the first eigenvector for lift. What that means for approximation, I could build an approximation of this collection of data, overlay my values of lift, and then all of the quantities for a proposed optimization problem where I'm trying to minimize drag subject to a lift constraint lie along the edge of the zonotope right here. So we basically visually quantified the set of all optimal solutions for this type of problem an engineer may be interested in. All right, so in summary, we found some cool stuff. We've got some future work we're gonna do, and I have some references. Thank you.
Great. Thanks, Zach. If you want to know more about how Zach is using these tools to build rocket ships, then I encourage you to talk to him later. Otherwise, we will move on to our final speaker, Mike Schmidt. Mike, also a PhD student. Actually, you're not a PhD student in this department, is that true? Or
no, I am.
This department? Okay, because I looked you up on the directory, and it said geology.
Really? Oh, yeah, funded over here.
Well, let's fix that. And by way of introduction, I'll ask you, what is your process for research in one sentence?
Do what Dave tells me to do.
All right. Mike Schmidt.
All right, I'm going to be talking about a kernel-based Lagrangian method for imperfectly mixed chemical reactions. I work with Steve Pankovich here in AMS, and Dave Benson is in hydrology. So, chemical reaction, I mainly work with the diffusion reaction equation. Your classic ways of doing this are usually Eulerian, the way you see most. These are grid-based methods, finite elements, finite differences. Also have particle and cell, which is kind of a hybrid Lagrangian Eulerian, where you can maybe move these around as particles on a fully continuous matter and then map them to grid points in between these time steps. Your Lagrangian methods are your fully continuous, where you're following around these particles rather than only observing them at grid points. The original one is a Gillespie algorithm. It treated reactions of probability, and that's based on their probability of collocating, but even that kind of implicitly makes sort of a well-mixed assumption because there's no real domain in this algorithm. But what I do is called reactive particle tracking, which we're about to get into. So just the background, we look at the diffusion reaction equation where you see this is the diffusion equation over here, and this is your reaction. This is for A plus B goes to nothing. You just don't consider the product in this. And this is in an infinite dimension, or an infinite domain. Dimension 1, 2, or 3, doesn't matter at this point, but we'll mostly be looking at 1 later. And the one thing to note in the well-mixed case, we do have an analytical solution. If concentration of A's initially and B's are equal to just one value, C naught, we get just an ODE here, which those should be D's. And this gets you the analytic solution, which you can see tends to 0, like slope -1 for late time there. Now, all these ODEs, they make this, you kind of assume, at least in an Eulerian sense, things are well mixed within your grid points, or to have that analytical solution, you assume it's well mixed instantaneously and perfectly for all time. These are non-physical assumptions, and real-world and experimental lab or column experiments tend to see this scaling of the concentration decay rate from time to the -1 to t to the negative d over 4, d being your spatial dimensions. That you don't see it in this analytic solution, but it really kind of trails off and slows down. The reason for this is, and this picture looks way better on a small screen. Formation of islands, anyway. When you don't have a lot of mixing, bringing your reactants in contact with each other constantly, you get this segregation of reactants, where you see if these are A particles, these are B particles. Initial time, you just have this wild, noisy distribution. You can see at late time, if you have a high concentration of A particles, you have a low concentration of B particles. And the same goes in the reverse. You can just see the holes in either opposite plot, where there's a lot of A's, there's not a lot of B's, and vice versa. You just get the segregation. It's for that reason reaction only happens at the boundaries of these islands, we call them. So you really don't have a full, well-mixed reaction occurring at all times anymore. Now, reactive particle tracking, this is what I work on. It's an extension of this class B algorithm. It incorporates that probabilistic reaction evaluation, and it doesn't require the well-mixed assumption. We don't have grid elements. We just move these particles anywhere, and they can be anywhere in the domain. They can be, you can have really noisy or inhomogeneous situations, and you also do get that self-segregation of reactants behavior we'll see in a little bit. But functionally how it works, you initialize the domain. In most of our examples, we randomly scatter these particles according to a uniform distribution. This gives us things like IIDness, which makes them easier to analyze. But as we move forward, we do operator splitting between our diffusion and reaction. Diffusion, we just move them by a random walk. We have this diffusion variance, comes from Fick's law of 2d delta t for this discrete case. And then reaction, as I said, happens probabilistically. So this is our probability of reaction for each time step. Probability, this bit right here is the probability that two particles will collocate in the next time step. Where if you have a density for your A particle and B particle, the probability of collocation, assuming that diffusion is symmetric, that there is likely to move one way as the other, is the convolution of those two Gaussians, which is a Gaussian with some wider variance. So that is that term right there. This omega c naught over n naught is kind of a calculation of the mass of one particle, and then which is related to the initial concentration, domain size, and number of particles you start with. And then there's your thermodynamic reaction rate and your time step. Now, because we don't need this well-mixed assumption, it is able to capture that scaling reaction rate, the slope -1/4 in one dimension. Here are those islands I was talking about. Comes from an RPT simulation. We actually see the segregation. If this big old island of B, see like 1 or 2 A's that are left in there that'll be reacted out very soon. And that's how that segregation happens, I guess, where you see the reaction will only occur at the boundaries because these things aren't moving around a lot. Now, the other nice thing about RPT is it can handle these heterogeneous concentration profiles more efficiently than your really highly discretized Eulerian approaches. If you have a really heterogeneous initial condition, you need a lot of grid points in your Eulerian methods. With these particle tracking algorithms, the more heterogeneous your initial distribution is, the fewer particles you need, which particle number is the main driver of computation times here. So the noisier it is off the bat, you would need more grid points for an Eulerian one, but you would actually need fewer particles, which is kind of a nice thing in these situations. And if you are doing advection as well, you don't have any numerical dispersion from these particle methods. All your upwind methods and such are always going to have that introduced dispersion, but the particles just go where you tell them to. Now, disadvantages. One is that the number of particles is not a modeling choice. That's calculated from the initial concentration statistics of your whatever you're trying to model in the real world. So you would have, say, autocovariance and cross-covariance between your reactant concentration fluctuations, and that would determine how many particles you need in this current way things have been working, and also resolution for small concentrations. If you're just, what I've been describing, when particles react, we just get rid of them, we kill the particles. And as a result, your resolution is only 1 over n for n particles. Now, there's a couple extensions that we've been improving. One is this particle number preserving reactive particle tracking, where instead of before, you calculate that probability of reaction, you basically compare it to a random number drop. And if that probability is higher, you kill the particle. In this one, we preserve particle numbers, we probabilistically reduce masses. So what we're doing is we essentially calculate a difference in mass based on the collocation probability of these two particles, their masses, and some other stuff. And you calculate this for given one A particle and maybe every other B particle in the domain. Each particle will take a little bit of mass from that one A particle, and this is how masses are reduced on a continuous spectrum rather than just on or off. Now that fixes one problem, and the particle number was a big one. This was my project, where we wanted to, before we were representing, representing these particles in space by Dirac delta functions, just a single point in space, no spread in space. And that gave us this very strict particle number. We wanted to see if there's a way we can use fewer particles. And the way we wanted to achieve that was to spread them out in space with a kernel representation. The main question here is what size of kernel, though, is optimal given a specified fewer number of particles. You want to pick less particles, see how many or how wide your kernel has to be to emulate this Dirac delta formulation. Now, this is kind of what I was trying to describe. I should have put the picture on the last slide maybe, but I think if you start out with a whole bunch of delta functions here, you would see the concentration curve is relatively even all across here. You eliminate some of those Dirac particles and you see it starts to kind of coarsen up the concentration. And to do that, we just superimpose Gaussians. We're using Gaussian kernels instead, which kind of re-smooths that concentration. It's not a perfect picture, but it kind of gets the point across. But the way we do this is we generate some stochastically perturbed moment equation ODEs that simulate this kind of stochastic reactive particle tracking. We use these equations to match our Dirac and Gaussian kernel ODE solutions. Then we take that value and use it in our particle tracking simulations. And here's just kind of a quick rundown of those moment equations. First, we take our concentrations, we assume, and we decompose it into domain averaged mean concentration, and then at each point in space and time, the fluctuations about that mean. Now, through all sorts of machinations, we get to this kind of nasty looking integral differential equation here, where C bar is your average concentration, P is either for delta or Gaussian particles, and you see this whole thing. The P just depends on this autocovariance function here, where for deltas it looks like this, you see your delta function in there. For Gaussian particles it looks like this, and you see your Gaussian function there. And that lives right there and is the only difference between those two functions for deltas and Gaussians. Now, in order to match these solutions, we do kind of a least squares exactly a least squares minimization, where we just minimize the two norm of the solutions here. We solve that integral differential equation there numerically. We solve it for a vector of times, and we try and minimize the error between those solutions, and that'll give us this LG star. That's the optimal, this parameter right here. Oh, this should have explained this. So the idea is you start with a certain number of delta particles, say 1,000, and you want to use 100 Gaussian particles. Everything else in here is a parameter of the system. Omega, mass of a particle is this one. But the only difference is this L, and that's what we're solving for on this next slide here. And that is the width of the half width of your Gaussian kernel that we want to know what would be the optimal size. So we do that. But I'm not going to go through the derivations, but in the paper we just put out, we do have an error bound. For T sufficiently large, the error between a Gaussian and delta simulation is bounded, where C1 is a combination of just parameters of the system. Delta is this, where you can see this number is always necessarily less than that number, so this is a small number overall. And it is a decent bound. And we also note that if you choose delta equals 0, which means number of Gaussian particles is the same as the number of delta particles, this error decreases with time, which is exactly what you want. It's just related to the initial statistics. Now, here's the punchline. We prove it with a picture. So here the blue is always our kernel solutions, red is always our Dirac solutions. The curves are the ODE solutions, those moment equations, and the scatters with the error bars are RPT solutions, just because we have to run 6 to 10 of these and average the results because it's a stochastic process. Where you see, and black is our analytic solution. Now for this first one, we use 90% of the number. We just use 1,000 as our base case for delta particles, and we use 900 Gaussian particles, where you see the solution is almost exactly the same. There's no difference at all. But what I thought was coolest was for an order of magnitude different, 10% of the particles, we get slightly different behavior at early time, but as we go to late time, there's almost no difference there. We're also, keep in mind this is a log-log plot, so even these differences aren't huge. A few other things about that we won't get into, but I don't know. Overall, I was really excited when this happened because, I don't know, then you're working on it for a year, it works. But That's about it.
Got time for a question?
Yes.
So like what spatial scales are you looking at, and what spatial scales are feasible to use this method? What do you think?
We just did it on like a omega 0 to 1. Like we wanted the particles there to kind of be a lot of particles in the domain. Essentially, it's just so that things would move around a lot at first, segregate as they went away, or as mass is reduced. But there's some papers initially that are written by my advisor where this does work all the way from the pore scale, column experiment scale, all the way up to the field scale, where this really does work across a range of scales. This was more just my little toy problem to get an algorithm going.
So when you say pore to field, can you give just like a length scale, like we talking microns, meters, like I'm guessing microns?
No, but I
small.
bet Dave would be able to give you a better answer.
The last thing we did was hundreds of meters. So, and then I've also seen the same things happen for like exciton mode movements in carbon nanotubes. So, down to from nanometers to kilometers.
Often, particle methods tend to be very expensive.
Yeah.
And so, especially if you have like larger time or space scales. So I'm just curious where you think this is efficient, feasible.
Yeah, well that's, there's this one advantage we talked about, the no numerical dispersion is the big one.
Yeah.
And also if you really have that heterogeneous profile, particle methods tend to shine a little more because the particle number decreases with how noisy things are initially. And that was also the whole point of kind of what I was working on, is how can we, for example, Dave's other PhD student, he had to use, I think, he had a few different species, he had to use 10,000 particles apiece for this field scale modeling exercise. And took him like long runs on this, but if you could impose these kernels and really reduce your computation times is kind of what we were hoping, what we tried to do here and think we achieved.
If you were going to approximate actual proteins, let's say you were looking at like protein fusion or something like that, would the radius of the kernels in any way relate to like physical size of the particles, do you think? Or does that not really matter?
Not necessarily, because as like for the Dirac example, it's related to the correlations between fluctuations of your different species. So the auto correlation, or autocovariance rather, of kind of just the distribution of your reactants in your domain. That's where that number comes from initially, and as far as I know, it doesn't have a direct size analog.
Yeah.
Something I kind of wondered when I was coming into this, and it seemed to not be the case. I always thought these were like particles that exist in actual fluid, but they're just particles.
And it didn't depend on the K, the rate either. So
Right.
It's interesting. Anyway,
This does sound like an interesting discussion.
Yeah,
I encourage you to continue it outside of the symposium here. So let's thank Mike one more time, and also thank Nick, Zach, Andrew. Great job, everybody. Want to just show you what happens next. So our very first colloquium for January will be Professor Roger Ghanem from Aerospace and Mechanical Engineering at USC. This will be a special joint colloquium with mechanical engineering, so we're pretty excited about this. So I hope you'll all have a great break and come back next semester ready to experience colloquium. All right, thanks so much.